Wheel, wheel, wheel. What do we have here? We have torque adding up to someone else's life. In this example, it must be something. Okay, what I want you to visualize, or what I would be able to tell, this is a bicycle tire with a force being applied that is perpendicular to a radius. All right, so a force that is perpendicular to a radius ought to sound familiar. That's torque. All right, so that mass, that force of gravity, is pulling down at the rim of this wheel, making it rotate, which is why it's accelerating, which is why I'm saying it's adding up to someone else's life. This one is adding up to something. That's a little different than the previous torque calculations where it was all in equilibrium. It added up to nothing. This time now, what makes this set of notes a little different is, well, this time it adds up to something, okay? And that's what it means by the torque and acceleration title for the notes here. All right, now Newton's second law is F equals ma. You all know that. That's easy. The rotational equivalent of that is the sum of the torques equals I alpha, okay? And so this drawing right here is what I was just showing you. The only difference is when we do this drawing, what we're going to say is the string is wrapped all the way around the wheel, and so as that mass falls, the force of tension in that rope will always stay perpendicular to the radius, okay? That's the only difference between this drawing and that example. That string will be wrapped around the wheel. Okay, so when it says spokes are light, what that means is you can disregard the eye of any of those given rods. All the mass is going to be out there on the rim, on the wheel, so this is going to act like a hollow ring. Okay, the mass of the wheel they give you is 4 kgs. That says they're going to be a little bit of friction in the hub of the wheel here in the axle, 2.5 Newton meters. Remember when they talk about a torque, it's a force times a distance, right? A Newton meter, okay? Don't replace it with the letter J though, because when a torque, it's a force times a distance that is perpendicular to each other, all right? A Newton meter that's replaced with the joule is when the force and the distance are parallel to each other, all right? Those are two very different things, okay? The mass of the hanging block down there that's making this whole thing move, that's applying that torque's 2 kgs. So this question then just says, hey, what's the alpha? The rotational acceleration of this guy as the mass is falling, all right? So the first thing we will do is pick an axis of rotation. Whenever you're calculating torques, you got to figure out what you're going in circles around. In this case, it's obviously the axle of the wheel, okay? So then we are going to sum the torques around that particular place. Sum of the torques, you know, is equal to I alpha. You can tell the rope is applying a torque a certain distance away, so there's the torque of the rope. From that, I'm going to subtract friction because friction, again, is trying to prevent it from rotating. And then this portion right here, this I, again, is the I of the wheel, just the hollow ring, which is mr squared. That stands for the mass of the wheel times its radius squared, okay? So just remember, I of a hollow ring, mr squared, and then there's the alpha, all right? So what I'm going to do now is break the torque into what it's made of. It's made up of two things, a force and a radius. So this is the force of the rope times the radius, the distance that that rope is away from the pulley, or from the axis, that triangle up there, minus the torque due to friction is equal to the mass of the wheel times the radius squared. So there's your mr squared alpha. All right, now, please do not make this mistake. Do not call the force in the rope mg, because it's not mg, all right? The force in that rope is not the mass times gravity of the pulley. If I were of the mass times gravity of the weight that is hanging there, it is not that at all. If I were to isolate that block, okay, the mass of that block, just ask the block, how many arrows are pulling on 2? It would say 2. There is the mass times gravity and the force of the rope. If they were the same, then this whole situation would equal my life. It would equal nothing. But The whole point of this set of notes is it equals something. It's accelerating. So if this item is in fact accelerating as it's falling downward, then the force in that rope has to be less than mg. All right, so what I'm going to do is figure out what the force in that rope is using the mass that is falling. So there's the mass that's falling. It's got mg and it's got a force in a rope. Those two arrows now, when I put them together, they will equal someone else's life. All right, they will equal something. So when I say the sum of the forces on the block, that will equal the mass of the block times the linear acceleration of the block, that tangential linear acceleration. There's two arrows that I add up for the forces. Gravity is down, but it's the direction of motion, so I'm going to call gravity positive. So it will be mg minus the force of the rope to equal the mass of the block times the acceleration of the block, all right? And specifically, it's the mass of the block times gravity. So there's an mg. All right. Now we're going to get the force of the rope all by its wee little lonesome. So the force of the rope is going to be the mass of the block times gravity minus the mass of the block times the acceleration, and that will equal the force inside the rope. Now, here's one other thing I would like for you to remember. We have one more swappertunity. The reason I made a point to say that that acceleration is tangent. It's the linear acceleration of the block that is tangent to the circle, okay? It's going this way. It's tangent to the circle, which means it's a linear tangential acceleration that is a radius away from where it's rotating around. So remember, a rotational quantity and a linear quantity are related by the radius, right? So a tangential acceleration in A is a alpha. So what is boxed in red is what I just wrote there. The acceleration, the linear acceleration is equal to r alpha. You know that, don't you? So this alpha will be multiplied by the mass of the block. It will be subtracted from the mass of the block times gravity. That's the force inside the rope. So that whole expression right there, these two quantities subtracted from each other is the force of the rope. Now, that force of the rope looks awfully similar to, holy shnikes, that force of the rope. So not only do we just have a swappertunity, we now have a swappertunity. So what is boxed in that orangish color, whatever color it is, I don't know, I'm going to call that an MBG minus an MBR alpha. All of that is what I wrote right there. I'm going to put that in parentheses, and now I'm going to go back to the black color that is that. So that R is that R. I'm going to subtract the torque due to friction. That will equal the mass of the wheel times the radius squared times alpha. Okay, now remember, the whole point is to calculate alpha, so they now have to play Beatles music. Those two guys have to come together. So I'm going to distribute the R. This will be the mass of the block times gravity times R minus the mass of the block times R squared alpha minus the torque due to friction. That equals the mass of the wheel times R squared alpha. Okay, so what I will do is just push the plus button, move that over, and we're just getting the alphas to come together. So the mass of the block times gravity times the radius minus the torque due to friction is the mass of the wheel times the radius squared alpha plus the mass of the block times the radius squared alpha. Now the whole point is to isolate the alpha. So I'm going to fish out the alpha, and I'm going to divide by everything that's not an alpha. All right? So just fish, that's funny, fish out the alpha. It's as mass of the block times gravity times the radius minus the torque due to friction is equal to, in parentheses now, the mass of the wheel, r squared, plus the mass of the block, r squared alpha. So just divide by everything that ain't an alpha. Then this ends up being the mass of the block times gravity times the radius minus the torque due to friction divided by everything. Whoops, here, I'm not going to write that. Who cares? Just divided by everything that's in those parentheses there. The mass of the wheel times the radius squared plus the mass of the block times the radius squared. That, I promise, is what alpha is. And so now it's time to put numbers where letters are. The mass of the block is 2 kgs. G is 9.8 meters per second squared. Ooh, I forgot the radius, didn't I? Did I forget to write the radius there? Holy shnikes, 2 times 9.8 times the radius. Jeepers, times 0.3 minus 2.5 minus 2.5 Newton meters, okay, times 0.3. So the mass of the wheel, 4 times the radius squared plus the mass of the block times the radius squared. All right, so MBGR. I forgot to write the R. G bars. This is, I promise, this is going to be 6.26, and that's radians per second squared. So boy, it's a good thing I just noticed that. My gosh. Now, what I will do is say, okay, that's really the happy answer. That's the acceleration of the wheel, the rotational acceleration. Now, what if I were to ask you what the acceleration of the block is, that linear tangential acceleration? We can do it one of two ways. What I just said, the acceleration is equal to Ralpha, isn't it? RA. It's 0.3 times 6.26. The radius times the rotational acceleration. The 6.26 here, let me write that next to, oh, come on, is, this 6.26 is in radians per second squared, okay? And it is 1.87, so that will equal 1.87 or 1.9-ish, and this is meters per second squared because it's a meter times a radian in the numerator per second squared. So 1.9-ish, a little less than 2. All right, now, what if we were to then ask you what the acceleration of the block is just by using those two forces right there? This is, again, you don't have it. I'm just showing you another way to get the acceleration of the block. Treat it like a Newton's second law problem because, jeepers, it's a Newton's second law problem. So all I'm going to do is show you how this gets us to the same place as 1.8, 1.9-ish. Summing the forces on the block equals the mass of the block times the acceleration. I'm just going to rewrite this equation down there, but I'm not going to solve for the force of the rope. I'm just going to solve for the acceleration of the block. All right, remember, there's two forces acting on the block, the mass times gravity minus the force of the rope. So it's the mass times gravity minus the force of the rope equals the mass of the block times the acceleration of the block. The mg is what we already know. That's easy. Now the force of the rope, again, was the mass of the block times gravity minus the mass of the block times r alpha. Okay, this equation right there is what the force of the rope is. I'm going to subtract that from the mass of the block times gravity. Okay, so that's where all those numbers come from. So now I'm just going to divide by that, and I will be left with the mg. Now the mass, this is the block. Now this is 2 kgs times 9.8. That's meters per second squared. Okay, from that I'm going to subtract in parentheses here the mass of the block, another 2 kgs. It's times 9.8 again. So right now it looks like I'm subtracting the same thing from itself. However, from this quantity I'm going to subtract the mass of the block, 2 kgs, but multiply it now by the radius, 0.3. All right, and this will be multiplied by what, 6.2, what did we say, 6.26 I think is what it was, 6.26. All right, and that's radians per second squared, radians per second squared. Okay, so all of that, so 20-ish minus 20-ish, but from that 20-ish I'm going to subtract 2 times 0.3, so 1-ish times 6.26, and then I'm going to divide all of that by the mass of the block, which is 2 kgs. All right, when you do that, I promise you get right back to 1.87-ish. All right, so that last part, again, I just showed you to say it does agree with what Ralpha shows us. And again, please remember, it was just a swappertunity right there, the Ralpha, and that's Swapper Tuna FFR. So it's the force times the radius that's perpendicular. Linear quantities and rotational quantities are related by the radius. You know that, and it was 6.26, and yay,